Welcome to chapter 4.2. 4.2 is about our trigonometric functions and the unit circle, okay? And you might recall from your trig in the past that we have 6 different trigonometric functions. They are sine, cosine, tangent, secant, cosecant, and cotangent. In this chapter, we'll talk about the unit circle and the relation between the unit circle and these trig functions. So, what is the unit circle? The unit circle is a circle that is centered at the origin and has a radius of 1 unit. It is generated by the equation x squared plus y squared is equal to 1. You might remember our standard form for an equation of a circle from the beginning of the year back in chapter 1. It was x minus h squared plus y minus k squared equals r squared, where h and k were the center of the circle. So in this case, our center is located right here at the origin, and we have a radius of 1 unit. And so if this circle has a radius of 1 unit, that means that this point right here on the circle would be 1, 0. The point up top would be 0, 1. The point to the left would be negative 1, 0, and the point down below would be 0, negative 1. All right, these points break up our circle into 4 different quadrants, into our 4 different quadrants of the circle. Now, every central angle theta in standard position means that our initial side is on the positive x-axis and the vertex is at the origin. Keep that in mind. Every single central angle in standard position has a terminal side with a corresponding point x, y that lies on the unit circle, right? So any angle that I draw, right, I can always have some corresponding point x, y that's located on this circle. Remember that positive angles are measured counterclockwise and negative angles are measured clockwise. So this right here would be an example of a positive angle theta. A central angle of 0 radians corresponds to the point 1, 0, right? We talked about our radian measure, right, on the unit circle. So, are there other angles that also correspond to the point 1, 0? And the answer to that is yes. And in fact, there are an infinite number of angles that correspond to that exact same point, right? 2 pi, that would be the equivalent of 360 degrees, all right? 4 pi, that would be the equivalent of 720 degrees, doing 2 complete revolutions. Negative 6 pi, that would be 3 revolutions in the clockwise direction, all right? So there are an infinite number of angles that share that exact same ordered pair as a point on the terminal side of the angle, all right? Now, let's take a look here. Notice that the coordinate plane splits the unit circle into 4 equal arcs of 90-degree increments, right? This would be 90 degrees here, another 90 degrees, and another 90 degrees, and another 90 degrees to get to 360. If 1 complete revolution corresponds to the angle 2 pi, as we talked about, what angle must each quarter of a revolution generate? Well, if we take 2 pi and we divide it by 4, we get pi over 2. All right, or 1/2 pi. That means each arc must rotate through pi over 2 radians to give us a quarter, all right, of this unit circle. So that means that the corresponding central angles in standard position would be, again, we start with 0. We have pi over 2, that would be 1/2 pi. We have pi, equivalent of 180 degrees. Notice I have 1/2 plus 1/2 plus another 1/2 would give me 3/2 of pi, 3 pi over 2. And finally, if I have 1/2 plus 1/2 plus 1/2 plus 1/2, that gives me 2 pi as coming around to a full revolution of 360 degrees. Okay? These angles are all known as quadrant angles as they terminate between the quadrants of the coordinate plane. Now, let's split the unit circle into 8 equal arcs of 45-degree increments. Okay, so notice I've taken each one of those quadrants and I've split it in half here, meaning that each one of these arcs is a 45-degree increment. So if 1 complete revolution corresponds to an angle of 2 pi, what angle must each 1/8 of a revolution generate? Well, if I take 2 pi and we divide it up between 8 equal arcs, 2 pi divided by 8, that turns into pi over 4. That means each one of these represents an angle of pi over 4 radians. Well, what does that mean? And again, we can count it out. We start at 0, all right? And the corresponding central angles in standard position would be, start at 0, I add 1 pi over 4, that brings me to pi over 4. If I have 1 pi over 4 plus another pi over 4, that's 2 pi over 4, which is the same thing as pi over 2. I add another quarter, 1 pi over 4, 2 pi over 4. This would bring me to now 3 pi over 4. I add another quarter of pi. That brings me to 4 pi over 4, which reduces into pi. I've got another quarter would bring me to 5 pi over 4. And then 6 pi over 4, which is 3 pi over 2. Then 7 pi over 4, which would be this angle here. And finally, if I add another quarter of pi, 7 pi over 4 plus another quarter of pi, that would be 8 pi over 4, which is the equivalent of 2 pi. All right, so again, we can figure out those angles just by counting out by fractions of pi. All right, the corresponding ordered pairs of the associated with each angle are root 2 over 2, comma root 2 over 2. And notice that when I go into the second quadrant over here to the angle 3 pi over 4, it's going to have the same y-coordinate. However, the x-coordinate is negative because it's in the second quadrant. We have negative root 2 over 2, comma positive root 2 over 2. As I move into the third quadrant, both the x and the y coordinates are going to be negative. That's negative root 2 over 2, comma negative root 2 over 2. And for this angle 7 pi over 4, which is in the fourth quadrant, my x-coordinate is going to be positive. My y-coordinate is going to be negative. Root 2 over 2, comma negative root 2 over 2 is the ordered pair associated with the point. So those are the ordered pairs associated with the point on the unit circle for each one of these particular angles. Okay, very good. So one thing to make note of, these points satisfy the equation x squared plus y squared is equal to 1, which is again our equation of this circle. So very important that they satisfy that equation. All right, so those were 8 equal arcs. Right? That meant every single little chunk was a quarter of a pi. Again, 1 quarter, 2 quarters, 3 quarters of pi, 4 quarters of pi, 5 quarters of pi, 6 quarters of pi, 7 quarters of pi, and 8 quarters of pi. We can also take each quadrant and split them up. All right. In this case, the entire circle would be split into 12 equal arcs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. If one complete revolution corresponds to 2 pi radians, what angle must each 12th of a revolution generate? Well, if I take 2 pi and I divide it by 12, that reduces into pi over 6. So what this means is that each arc must rotate through pi over 6 radians. Accordingly, the corresponding central angles, can ignore that second the, all right, the corresponding central angles in standard position would be, my first angle here would be 1 pi over 6. I go and add another pi over 6, that brings me to 2 pi over 6, which reduces into pi over 3. So 1 pi over 6, 2 pi over 6, 3 pi over 6. Well, 3/6 is 1/2. That's 1/2 pi. 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6. 4 over 6 reduces into 2/3 of pi. 4 pi over 6, 5 pi over 6. Again, we're just counting by fractions of pi over 6. 6 pi over 6. 6 over 6 reduces into 1. 7 pi over 6 for this next angle. 8 pi over 6, which is 4 pi over 3. 9 pi over 6. That would be 3 pi over 2. 10 pi over 6, which would be 5 pi over 3. And 11 pi over 6 here. And finally, to do one complete revolution, we would get to 12 pi over 6, which reduces into 2 pi. So the corresponding ordered pairs associated with each angle are, we have the angles. Now we need to know the ordered pairs of the corresponding points. With pi over 6, the corresponding ordered pair would be root 3 over 2 comma 1/2. The corresponding ordered pair for pi over 3 would be 1/2 comma root 3 over 2. Notice that when I go into the third quadrant, I have the corresponding ordered pair for the second quadrant, 2 pi over 3 would be negative 1/2 comma root 3 over 2. Take a look. If I go directly across, the y coordinates here and here are exactly the same. The x coordinates are opposites. So if I go to 5 pi over 6, the corresponding ordered pair is going to be negative root 3 over 2 comma positive 1/2. Again, y values directly across are exactly the same. X coordinates are opposites. 7 pi over 6, notice I go down. The x coordinate is going to be negative. The y coordinate is also negative. Negative root 3 over 2 comma negative 1/2. I go to 4 pi over 3. That's going to give me negative 1/2 comma negative root 3 over 2. And I go into my fourth quadrant now to 5 pi over 3. The corresponding ordered pair would be 1/2 comma negative root 3 over 2. And the corresponding ordered pair to the point associated with the angle 11 pi over 6 would be root 3 over 2 comma negative 1/2. All right, so these are all of the ordered pairs associated with each one of those angles and the points that they generate on the unit circle. And as we said, they have to satisfy the equation x squared plus y squared is equal to 1. Because again, that's our equation of our unit circle, and every single point on this circle has to satisfy that equation. All right, so there you have our unit circle, and here is a completely drawn out unit circle with the most common angles that you will see in trigonometry, okay? Make sure that you are familiarizing yourself with all of these special angles that you see here on the unit circle, as well as their corresponding ordered pairs. All right, this is something that you just need to memorize. All right, these are the most common angle measures and their corresponding ordered pairs, and you must take the time to memorize the unit circle in order to maximize your efficiency in trigonometry. You do not want to rely on having to constantly go back to look at the unit circle. You will not get anything done. So make sure you memorize it. Again, it will save you valuable time. You have to know it. You have to memorize it. No, I'm not kidding you. Know it by heart. All right? Memorize the unit circle. This is like the equivalent of your basic multiplication tables for trigonometry, right? Make sure you know them. All right, there we have our unit circle. In the next videos, we'll talk about how we are going to use the unit circle to help us in evaluating our different trigonometric functions.